Storm applications. Storm use case includes stream processing, which is direct stream processing without any intermediate queues, and also distributed remote procedure call, DRPC. Computation load is efficiently distributed over parallel processing CPUs for real-time reliable results. Continuous computation. Continuous real-time updates to a computation as the input streams are continuously analyzed and you get continuous outputs of what that computation results in. These are some of the major use cases of Storm. Real-time analytics, online machine learning, continuous computation. Also, we just talked about distributed remote procedure call. We will talk about more on this. And then extract, transform, and load operations. We'll talk more about this also. These are the main applications of Storm. Looking into further details, the DRPC. RPC, Remote Procedure Call. This is a program that can execute its process on a remote computer that is based on a different IP address. Distributed RPC, executed in a distributed parallel form over a cluster of nodes, is what the DRPC will do for Storm. Then we have extract, transform, load, ETL. These are the three essential database functions combined into one. ETL functions extract data from a database, transforms it, and then loads it to a data warehouse, where you can find the words of ETL inside here in its definition. Financial services are some of the major Storm applications, which include security fraud detection, policy violation detection, stock monitoring, alert notification, pricing control and adaptation. Then retail services, where logistics scheduling, sales monitoring, discount rate control, coupon distribution, shrinkage and stock outs, pricing and offers. All of these, as you can see, they need very fast updates and can change very rapidly because retail services are happening over the world in real time in so many different places. To monitor and include all the changes that have been done, all the new transactions and sales that are going on, well, Storm can support that very well. Web services, web server and system support, security breach monitoring. Of course you want immediate response detection on this security breaches. That's why Storm is most appropriate. Application failure recovery, user problem solving, personalized content protection. In the ICT and telecom services, social network services, once again, this is exactly why Twitter uses Storm. Mobile apps and cloud services, custom services, security breach monitoring as well. And network outage, such as from gateways, routers, and switches being malfunctioned, being hacked, being attacked by DOS and DDoS attacks. Typically, how to recover from that? We can use Storm very effectively. And of course, bandwidth allocation, giving the right amount of bandwidth to the throughput to the right locations. All of this can be controlled very effectively using Storm. And then there's mobility support and radio access network connectivity. These support mobile users that are moving around, and the network needs to adapt and change to support the mobile users, and also on other devices they need to reconfigure, send information, reroute the data so that the user can effectively get his data connectivity. All of this is needed to be supported by mobile devices, smartphones, as well as transportation systems. Understanding Storm using a comparison with Hadoop. First, cluster operations. Let's start big and then focus in down. Hadoop cluster, this runs MapReduce jobs on the Hadoop Distributed File System, HDFS. Storm cluster will run topology processes based on the DAG. Comparing process ending. In Hadoop, MapReduce jobs end when the assigned data set is completely processed. However, in Storm, this is an ongoing process. There is no definite end. Topology processes streaming messages continuously until the stream is intentionally terminated by the user. Node types in Hadoop, we had name nodes and data nodes. The name node was a master node, and the data node was a worker. And the name node runs the job tracker daemon, and the data node runs the task tracker daemon. In Storm, we have a master node and a worker node. A master node runs the Nimbus daemon, where the worker node runs the supervisor daemon. Now we will look at a Hadoop URL retweet counting example. This here is where the Twitter firehose provides streams of Twitter messages that need to be queued in an intermediate message broker node that serves as an intermediate queue. The worker collects and stores data in HDFS. MapReduce reads from HDFS to find web URLs is used. Mode hashing, which is modular hashing operation, and this will be such that you can select the right node, worker node, to give the right key and value information that is based on counting a certain URL. So therefore, the same worker node needs to do the same counting so that an update count can be provided by that specific worker node. And that is where the mode hashing is used in this system. Updated URL counts and statistics can be collected and sent to Cassandra. For example, you look at this system, and we're going to go over the details of what we just explained by the procedures. First, Twitter starts to give in its Twitter information through the Twitter firehose. This information needs to be queued because we don't know how fast it will come in. And if the MapReduce engine is overloaded, then we may lose something. There may be an overflow. So we need good-sized buffers, queues, to stack them up at the input size. So these queuing nodes are the message brokers. And they're there such that we don't have any missing information because of an overflow into the MapReduce engine. Then we have Hadoop, where we have MapReduce process, and then we have mode hashing, such that we assign the counts, the key, and the values that are processed through MapReduce to the right devices, the counters, and also the counters may get overflowed. So just for that, we'll have in the beginning part of the worker nodes, there will be queues, and then there will be counters, and then the result could be sent to Cassandra for savings. This is a mechanism that was used by the original Twitter engine. It uses Hadoop in the middle, where in this middle part, taking a look into it, it is HDFS, MapReduce, HDFS, MapReduce, HDFS, repeatedly processed. And in some parts, there are iterative processes that will go around in a loop structure. Looking into the details of how this worked in terms of topology and speed, well, you can see that iterative part where you will have data on disk that will be brought into it, and a map function will be processed, and then it will be saved back onto that hard drive disk. Then it will be taken back up again, read again, and then the reduce process will be done, and then we will put it back to disk. Now, as in the former lectures, as I have explained, this read and write from hard disk drives are slow. And you're also doing this for a large amount of information. And also above, you see in the red box, this is an iterative process. I need to do this over and over again. For this case, this will slow down the analysis and making it maybe too slow for Twitter, because Twitter tweets are going on worldwide at a massive speed and a massive amount. That is why we face some issues with Hadoop. Intermediate message broker functioning queuing nodes are needed because we don't want to overflow the MapReduce engine. Read and write with HDFS is slow, so multiple HDFS read-writes will even be more slower. Needing to compute the mode hashing operation, this is cumbersome. And to send the same URL message to the same counting worker, this is also inconvenient. Then again, adding an additional worker node, if you want to expand your system, if you want to grow, then you will need to add a new worker node, a new data node in parallel to the existing system. Then you will have to do a lot of additional programming. Let's say in the Java Virtual Machine program, JVM programming of the worker nodes, the data nodes, and then you will have to put them into the system of the cluster. Significant time is required to conduct programming replacements throughout the cluster. In addition, Hadoop program for this job is complicated. It is difficult to program. In addition, it is difficult to debug. So let's see how Twitter changed to Storm and to do this process in a more effective way. Here, Storm will receive Twitter messages in tuple stream form, and multiple bolts in parallel are assigned to the task of finding the URLs and counting. The following stages of bolts aggregate the URL counts to find the summed overall final numbers. The final stage bolts will have the Twitter URL statistics saved to Cassandra. Looking at this in action, well, Twitter has their tweets and their records feeding into the system through the Twitter firehose. We have spouts that are the receiving parts of it. And then we have the bolts that are actually doing the transformations and the counts. Look right here. There is no queue before the spouts. Why? Why is this possible? Why do we not need queues before we have those spouts? Is there a reason for that? Just wait one second. I will explain that to you. The transformations, the counting operation is done in the bolts, and they are collected, where the final result is saved to Cassandra. Advantages when using Storm. Here we go. Spout controls the message input stream from Twitter. It is using a pull-based scheme, and this is different. In other words, when you are passively receiving something that is being sent to you, your queue, you may be overloaded. You may be full so that whatever comes after you're full, then you will just lose. It will be an overflow loss. Here, the spout, that is the input data component that controls the flow into this network of Storm, is based on a pull mechanism. It will bring it in. What does that mean? I'll give you more details on this. Just wait. Guaranteed data processing of all tweet messages. Now, there is reliable and unreliable spouts and bolts, and we will need to talk more about that. If it's reliable, then the operations are even more guaranteed. Where unreliable spouts and bolts, there could be some misses. Not much, but there occasionally could be. We'll talk about more on this. Built-in self-healing fault tolerance capability is also included in Storm, as well as no intermediate queuing nodes are needed. No mode hash operations are needed either. Great horizontal scalability of spouts and multi-stage bolts are provided through Storm. Fast RAM-based in-memory read and write speeds are processed in the bolts. So in other words, instead of using hard disk drives, we're using as much as possible in-memory RAM. And once again, RAM is about 100 times faster per process compared to HDDs. And we've already studied that in former lectures of this course. Please check that out again. Simple and easy program debug and upgrades are possible. And instantaneous processing topology updates with the rebalance feature are possible as well. This is great because once again, one of the problems when we were using Hadoop was that if you wanted to add in an additional worker node to help and grow the overall system, then you would need a lot of complicated processing, a lot of additional programming, and then interfacing with all the other nodes. Change their programs as well. That was complicated. But here we have the rebalance feature, which can instantaneously give us a swap-in programming capability. We'll look into more on that. These are the references that I use, and I recommend them to you.